Hello all and welcome back. So in this video, let us now continue our discussion and now let's move forward to different traversals which we can do in our graph. Now, if you all remember in a tree, which we now know is also a kind of a graph, we had different way of traversing our particular tree, right? So if I make a tree here, like this is the one node, then let's say it's a normal binary tree. Right? So the way we saw, we were able to overall traverse our tree or something like this. Let me make it a little nice so that your notes are great as well. Let us make a full circle and let us try to copy this off. So the way we saw, let's say if this is our tree, everyone, then we were able to traverse our tree in a way that we were going to one of the nodes. We used to ask it to print and then call recursion on others, right? So that was one way of traversing our whole tree. Now till now we have seen that how can we showcase how our graphs look like. So we use something like that, right? So we have this A vertex, then what all is there after A. Or let's say in an adjacency matrix, we were able to print that whole out. But in traversal, we have to make sure that we are traversing our graph, okay? Just like we used to do here. All of you would remember how we did multiple traversals on tree as well. So the idea is the same. I will be given a graph, right? So we will have a graph. Let's say this is a graph which we have. Now, in this graph, I have to make sure that I can traverse it overall by just going to one of the node and then asking that to traverse on rest of the graph. So we can again very well use recursion here. Now, let us move a little forward and see how exactly or what are the different kind of traversals which are present here. And again, these are very important to understand. The reason is that most of the question in your graph will be done if you understand these traversals pretty well, because these questions are these algorithms or traversals are the major one which we use. So let us move to the first one, everyone. That is known as depth first search or DFS. The name might be seeming a little heavy, or you might be thinking that okay, this is some very big algorithm or something, but actually we have done the same in trees. Okay, in trees, let me just copy that trees and show you how the DFS traversal used to be like. So if I'm copying this whole tree, everyone, if you all remember, right, as the name suggests, DFS, depth first. In our tree, we used to print this out, the root, and then used to call on this leaf. Sorry, this node. Then it used to print itself out, then go to this node. So in our pre-order traversal as well, if you all remember, we used to kind of do a similar thing where we used to go in a particular depth. So at a particular depth, we used to go, then used to come out, and then towards the other side, we used to go in the depth, right? So the idea is that I will be picking up a node. We'll see, okay, who all this node is connected to, who all are its neighbor, right? Once I get its neighbor, then what I have to do? I have to make sure that I call on that neighbor. So if I have to just tell you, or if we just see that what will be the DFS traversal of the graph, which is with me on the left. Let's say I start with 0. So we will have to have a starting point. I will first go on 1. Then 1 will call on 2. 2 will call on 3. 3 on 4. Now 4 is connected to 2, but we have already visited that. 4 is connected to 3. We have already visited that. Right? So again, we will not be going back there. And we will come all the way back to 0 and then print 5. So the traversal of BFS is going to be something like this. DFS 0, 1, 2, 3, 4, and 5. Now the reason we are going to 1 first and not 5, so we could have done this as well. Again, 5 is also a neighbor of 0 only. It's just that we will be starting our loop. In this also we will be writing a loop which starts from 0 and goes till number of vertices. So it will be starting from 0, then we'll go to 1. 1 will try to go to 0, but it will see that okay, it has been visited. Then 2, then 3, then 4. Something like this is going to happen. Okay, great. So I hope the basic idea about depth first search DFS is clear. If I be really honest with you, most students may find it a lot difficult, but I think it is very easy if you just try to understand it once and try to code it at your own. Okay, even after understanding with me, then believe me, it is very easy. Like we understood how exactly this is going to happen. We have done a similar kind of a thing in a tree as well, right? And in many questions, we will be doing and using this kind of a traversal, depth first search, right? So let us now go to VS Code and try to code this out, everyone. So this is our graph using adjacency matrix. Let me just do one thing. Let us make a new file. Here be graph traversal, which is dfs.py. Great. So I've just copied the whole graph down again. So what we can do is we can create a function here, which is bfs. Sorry, DFS. So anyone can call this function and it should be able to do the overall depth first search on my algorithm, right? Sorry, on my graph. Great. Now let us try to code this DFS algorithm, everyone. See what are the different things which will be there in my DFS algorithm. First thing, as we discussed, we should have a start vertex, right? We should have a start vertex, which in this case I am taking 0 normally. So should be fine. We are just taking the start vertex as 0. If the user provides that, we will start with that. Great. Next thing, let us say that we are having this result. Okay, so we are maintaining this result. We will be printing the same as well, but we are maintaining this result as well. Okay, it's an empty list initially. Then all I'm doing is I'm just calling another function. So DFS, okay, recursive. I'm just calling this function. Whatever is the start vertex, along with that, I'm passing this particular list. Okay, great. This function we can make another function here. Just going with respect to oops. Let me zoom it in. Or I think zoom out is better. Should be fine. Create some space so everything is clear. Great. So DFS recursive self vertex starting vertex and it is getting a DFS result. Great. So as of now, what I've done, I've just maintained this DFS result list. Again, I'm using this list as well because in many places you might have to create this list, right? So I want to make sure that you never feel fearful of this thing. It's just a list which we are passing. And in recursion, we have seen this already. When you used to pass a list and all the result used to be there. Great. Now let's say I'm on the starting list, right? I am on the starting vertex, which is 0. What should I do? I should just print it out, right? So what I should do, print whichever vertex are we on. So print this vertex. Great. Along with that, let us add that to our result as well. So along with printing, we are maintaining an order in our DFS result as well. Once this is done, once I have printed 0, then what we should do? We should now see what are the different neighbors of my 1, right? So what are all different neighbors of 1? Sorry, of 0. 1 is a neighbor, 5 is a neighbor. How can we check that? We have a very good adjacency matrix with us, right? So using this, we can check the same. For example, pay attention. For neighbor in range number of self dot number of vertices. So I will be going through each and every vertex and check if the neighbor, okay, if this vertex is a neighbor of my current vertex. Great. Very first thing, if vertex equals neighbor, then I think we should continue. Why is that? When it will be 0, when it will be 0, the neighbor will be 0, it will be starting from range, right? Then I should not be checking this for 0 to 0. So what I meant by that, pay attention. Initially, the start vertex I'm saying will be 0. I will be passing the start vertex and I will get 0 here. Now I am running this loop. Let's say it runs from 0 to 5. We have 6 vertices there, right? So 0, 1, 2, 3, 4, 5. Initially, we will see from 0 to 0. Now, it is not required, honestly, because we have this no connection edge in the adjacency matrix as well. But I believe that it is very useful to write because tomorrow, if by chance this will be required, you will remember that, okay, something condition like this is present. I don't need to check if 0 to 0 there is an edge. There is not. Okay, great. So let us move forward. This is the first thing. Second, now if, pay attention everyone, how this will be. Self dot adjacency matrix of vertex and neighbor equals 1. Now what I'm saying, for 0 to 0, this will continue. Next we will go to 1. Hey, is there an edge between 0 and 1? If it is, if edge is there, then what we have to do? We have to do something, right? What we have to do? We have to just call our DFS. So DFS recursive, we have to call on this particular neighbor, and we will pass our DFS result as well. Okay. So again, I will just explain what we have done in this particular code. Let us take an example. So 0, 1, 2, 3, 4, 5. Let us take the same example, everyone. Let me just remove this here. So what I'm doing is, this is my 0. This is 5. This is 1, 2, 3, and say 4. Okay. They are also connected. What I effectively did, I started from 0. I printed 0 out. Then I said that, okay, I'm just maintaining this DFS result as well, just to make sure that in future you have an idea how to maintain the result in a list as well. I called recursively with the starting node. 0 now checks what are all its neighbor. And we have something like adjacency matrix like this, right? So 1, 2, 3, 4, 5, 0, 1, and it will be like this: 0, 1, 2, 3, 4, 5. So something like this adjacency matrix we have, everyone. Now what will happen? Pay attention. Once I go and check for this neighbors of 0, again, when it is 0 already, then we don't have to do anything. So we can continue. Now we will check for 0 and 1. Okay, so now we are going to check for 0 and 1. If there is a edge, then this particular adjacency matrix will be equal to 1, or at least greater than 0 if it's a weighted overall graph. So something will be there. We can have this condition as 1 minute. Yeah. So we can have this condition as greater than 0 as well. Okay, or not equal to 0 if it's a weighted graph. Then what I'm saying is, okay, now call on 1. Now 1 is going to check what are all its neighbor. It will go and check, okay, what are all the neighbor, and ID should go to 2. So let us try to see what exactly is going to happen here, everyone. Let me just run this, not removing anything because it will be helpful. First, let us try to make this graph. Okay, so we have 6 vertices here. Let us try to make this 4 and 5, E and F. Edges between 0 and 1, 1 and 2. Then we have an edge between 2 and 3. Then we have between 3 and 4. Then we have an edge between 2 and 4. And finally, we have an edge between 0 and 5. Okay, so I think these are the 6 edges: 1, 2, 3, 4, 5, 6, which we have added. Instead of graph.bfs display, I'm just using DFS. Okay, great. So let us now try to run this, everyone. See what is happening. Okay, so I see a lots of 0, 1, 0, 1, 0, 1, 0, 1. It did started with 0. It went to 1, but then it went back. So something we have made a mistake, right? Let us try to understand this. Code is stopped, so it should be fine. Yeah. Great. So what happened? Let us try to understand this, everyone. In a way, we made a mistake. The mistake we made was, I hope the blue color is visible. Yeah, it is. Let me make 1 minute. Let us check red color. Okay, so let us see the mistake with red color. We started with 0 and we said that, okay, call on 1, and we went to 1. That's why you saw 0 printed and then 1 printed. Then 1 checked all its neighbor. It checked, okay, if 0 is a neighbor or not. For 1, 0 will be a neighbor, right? I hope all of you are able to understand this, that for 1, 0 is also its neighbor because it's a undirected graph. If 0 is connected to 1, 1 is connected to 0. So 1 made a call back to 0. Then again, 0 made a call back to 1. 1 made a call back to 0. And in this way, we just kept on oscillating here. infinite loop, right? We kept on making this call. You are seeing 0, 1, 0, 1, 0, 1 on your output as well. What we missed out was to make sure that we maintain some visited list. We should tell one that, hey, we have visited 0 already. Please don't go there. Okay. So let us make that, everyone. Pretty straightforward. I hope you got the idea. Now, why this was not required in tree is that we had a particular hierarchy there. We used to check for the children and make a call on that. Children had no way it can go back to its parent, right? So it was in a way directed from parent to children. If you will remember, let me remove all the thing now. Great. If you will remember, we used to just call from this child to parent to its child. There was no way it can go back, and hence we didn't use a visited array then. But in this graph, there is a way through which your one node can go back to the another node and again back. Hence, what we have to do now? Let us maintain a visited, which is going to be false initially for my number of vertices. After that, I can just pass this visited as well here, because again, we have to make sure that we keep on passing this overall list. Either we maintain it outside somewhere, but I think it's better if we always try to just set it up, because else if you try to maintain it here, if any one of you are thinking to maintain it here, then once you do the BFS, everything will be visited and you will not be able to do it again. Okay. So I have to maintain and initialize it every time. We have passed this visited. And now, anytime you visit a vertex, let us make that vertex equals true. So for 0, it will get true. Okay. This time when we will check if self.adjacency matrix is 1, so if it's a neighbor, and if visited of neighbor, if we have not gone back to that neighbor, if it is false, then only call for recursively. Okay, I hope each and every one of you are able to understand this. What exactly have we done? We are maintaining a visited. This visited we are passing. Anytime we print a vertex, we basically go or traverse on this vertex. We will say that, okay, you have been visited now. Now, when we check for this connection, we only make a call for two conditions. A, there should be an edge, and B, it should not be visited. So now when the contour will go to 1, it will find an edge between 1 and 0, but it will not make the call because it has already been visited. And hopefully we should see this particular output. Let us try to run this, everyone. Okay, we are getting an error. Let us see what the error is. Missing one required positional argument, which should be visited. And we are able to see the results. 0, 1, 2, 3, 4, 5. Okay. So 0, 0 to 1, 1 to 2, 2 to 3. Because again, we will be starting that loop from 0 to 5. Okay. This particular loop. For neighbor in range self dot num vertices. So 2, it doesn't have an edge. 2 doesn't matter. 1, it has an edge, but 1 has already been visited. First 3 will come, so it will call on 3. Then 3 will call on 4 with a similar mindset. 4 will see that, okay, it has an edge with 3, but it has been visited. It has an edge with the 2, but it has been visited. So we will return. Once we return, we will just go back here, backtrack, and then at 0, we will again check. If 5, it will now check for 2, 3, 4. We don't have any edge. Okay. For 5, it will have an edge, and thus we will see that yes, edge is there, it has not been visited. So it's a good idea to go and visit and complete our traversal. So that is the whole major idea, everyone, with respect to the DFS traversal. Pretty sure that you must not have find it a lot difficult. It just, we are using recursion, and you know that in recursion, in a way, stack gets used, right? So in recursion, all the functions, they are getting called and maintained in a stack. So here we can also say that we can use a stack to do a DFS traversal of my graph. Very important is to maintain this visited list as well. Okay. I have shown you without visited list as well that what will be the problem. So instead of directly using that initially, I wanted to make sure that you understand what is the error which you can get if we don't use this visited. Okay. So great, everyone. I hope this is clear. Now your work again is to make sure that you are able to code this out yourself without just referring to the code. Try to understand from this video and code this yourself. because it is going to be a lot helpful. If you are able to code your DFS yourself, you will be able to do lots of question in your graph going forward, because these traversals are the major algorithm which are used in graph question. Even in companies such as Google, Amazon, Microsoft, Goldman, any other, any like all these companies will be asking you questions on graph majorly where a algorithm like this traversal is going to get used. Okay, so I hope that all of you will be now able to code this from scratch very comfortably. Great everyone. So now let us meet in the next video.